Welcome, everybody. It's good to connect with you today. We're working through the bioenergetic platform of basically the I like to call it a platform because it's really kind of a thought form, a mind stop. It's a a consideration that stimulates us into action towards how living systems work. So today we're going to talk about how and what a plant eats. But I wanted to show you this graphic. It's just something that we worked up that we provide for people as just kind of a broad stroke towards the fertility management services that we conduct. We do soil and water testing and survey-based recommendations for basically every aspect of agriculture: pasture growers, hydroponics, container gardens, lawn care, farmers with and without irrigation, etc. And this just kind of gives you again, a broad stroke of the things that we consider. And just scanning over this flow chart here, you can get an idea of some of the things that we may be looking at that aren't on the radar of general consultation or extension-based consulting from a conventional and even organic perspective. I think the things that are unique are the energetic component of life. It's something that we spend a lot of time talking with people about, and we're all generally aware of it without working with it. The exchange capacity in the soil's electrical. The sun's energy. Active transport, uptake of fertilization. Something that we'll talk about a little bit today is energetic. Life is energy. It's easy to get caught up in the differentness of biodynamic methods and life force and these kinds of terms, but on a very basic sense, there's something that separates life from things that are not alive. Living organisms act differently, and any attempt to measure them is simply a snapshot. I mean, in all reality, how's one to measure what you are? You're more than the sum of your parts. Doesn't mean that we can't identify those parts and gain some value out of it. So it's kind of a trust but verify sort of approach. So we evaluate the soil physical properties through remote site generation. We look at the mineral component through the soil testing and base saturation, the biological through the food web identification and compost teas and composting and the energetic. And you end up, this a lot of agriculture gets boiled down to a plant fertility conversation without taking into account the context of what a plant's working with. And we miss a whole heck of a lot. So, this idea of kind of looking at this from a big picture gives us a means of articulating these different capacities over time and learning more about them, and therefore influencing our agriculture accordingly. And so, you probably picked a little bit of that up as we've gone here, talking about the physical and moving now into the mineral component of bioenergetics. So today we just want to really focus on how a plant eats and what it eats. In general terms. And then, next week we're going to get into a comparison of organic fertilization versus hydroponic, which I've always found to be a really good way of kind of teasing out some of the similarities and also some of the differences, and why each may make sense in a different application. So this is a general statement. Plants eat through their leaves and roots. Some people might not be familiar with plants eating through leaves. We're going to talk about that a little bit. Plants are autotrophs. They can generate their own food. They can, fix an inorganic carbon primarily through the air, right? What most are familiar with in terms of photosynthesis. We covered that in past weeks in some detail. compared to animals, they're heterotrophs. They cannot fix inorganic carbon and seek out organic carbon sources primarily through plants that have fed animals, and if you're a meat eater, animals as well. But we can't make our own food, right? So one way of looking at this is plants don't move, right? And there's always outliers, but generally that's a true statement. One outlier being nastic movements in plants. You may have seen these mimosa plant, the sensitive plant, whatever you like to call it. It's pretty amazing to see that happen. It's basically a response to a stimuli, and it could be like the mimosa plant, that immediate shriveling of the leaf. It's quite impressive to see that because we're not really used to seeing plants move. We stretches the patience to sit there and watch it. I've had indoor grow rooms with carbon dioxide at 1,600 parts per million, controlled environment, and I could swear that sitting there with enough focus, I could watch the plant grow. I mean, you certainly can from a couple hours to the next, coming back and checking it. You can even see this through the day of the sun moving through the sky and the plants following it. So an extreme example is, and it's one that's particularly relevant to me where I live, is the Venus flytrap. You have this, I'm going to show you a video, which is kind of amazing. But if you're unaware, I mean, everybody's heard of a Venus flytrap. Maybe Feed Me Seymour, depending on where you heard about it. But the only place on Earth that they're native to, where they grow endemically, is about a 75-mile radius around Wilmington, North Carolina, where I live, southeastern North Carolina. It's a coastal community. And we have around us quite unique conditions. It's kind of in between a tropical and it's a zone 8, but it's more like 8.5. We're kind of the last remnant of where a palm tree can grow, and they struggle. 3 hours south in Charleston, they thrive. So we've got this little unique microclimate here, and it's really kind of fascinating to see these guys. You can go out in Carolina Beach State Park and see them growing in the wild. So I'll show you this video real quick, and we'll talk about it.
The Venus flytrap. Like the sundew, it makes itself very beautiful, at least to a bug, oozing fragrant nectar across the surface of each leaf. The eating's good here, but any visiting insect had better watch out for these 6 tiny hairs. This fly doesn't know the game is rigged. If it strikes one of these hair triggers, it can carry on feeding. But that contact activates a 20-second timer. A second contact while the timer's running, and an electrical impulse is triggered, and the leaf snaps shut in a fraction of a second. The tips lock together like prison bars. If the fly is very big or very small, it may just beat the rap. But most get the death penalty. Ten days later, the trap reopens. that remains is a desiccated husk. The plant has finished its meal and once again sets the table for the next victim.
If you're like most red-blooded humans, you visit Florida for the super fun theme parks.
So,
But may I...
sorry about that. So that's quite amazing, isn't it? It's notice the electrical impulse, right? I mean, you can't get away from the energy there. But the fact that the plant digests an organism, that's a total outlier to the plant world. Just goes to show that anytime you try to compartmentalize nature, you lose. But it's fascinating. These plants, when I first learned that they were the only place in the world they were from was here, I didn't believe it. I thought the Amazon would have kicked out something equivalent. And they've been introduced in other areas, like in Florida and I believe some other areas. But the fact that they come from here is really a phenomenon. And then the Nature Conservancy actually spent a lot of resources and time years ago trying to investigate, what was the source of that in this environment. And they quite strangely and amazingly deduced it down to an asteroid that hit in this area millions of years ago. And they created what's called Carolina Bays. There are these little circular pools of water they've come to be in the middle of the forest. And it's just basically the craters from this impact. And the working theory was that some kind of material was brought. I don't know that they really surmised that the flytrap was brought here, but it changed the local environment in a way that stimulated this quite impressive development in plants. So if you've never played around with a flytrap, they're fun to keep at home. They actually grow on looks like a garlic clove. It's called a corm, and you can separate them apart and repropagate them. And that's typically how commercial Venus flytrap operations work. They have a permit. So when a parking lot's coming through, they can go in and extract whatever's there, and then they use that as a source to clone these plants out and have them for sale. And there's the guy who put up, years of his life into lobbying for the flytrap locally, was given the honor of a namesake on a park here. And this was a couple of years ago. And they didn't have adequate security. And about 2 months after it launched and was introduced to the public, some people were found robbing this area of these flytraps because they're obviously quite valuable, as unique they are. And as they are, they, after that incident, changed the law in North Carolina. It's actually a felony to extract these plants. So, bit of an aside, but, it's always interesting to kind of explore the caveats, and the outliers of the things that we're talking about. Venus flytraps like really poor environments, really boggy type environments that are minerally inert, peat moss kind of thing, and they get all their nutrition through plants. So anytime someone tells you that a plant can't eat anything other than the food that it makes for itself, there you go. So the leaf, to talk about that, plants eat through their leaves and through their roots. This is just a cross section of a leaf. You can see the stoma and the guard cells and the epidermis and the layering of the leaf and the xylem and the phloem through the veins. This is kind of a simple schematic, but it's worth talking about the stomata, singular being the stoma. Again, plants do move, just not on a scale that we're used to identifying. There is a literal intelligence there, for lack of a better word. The plant regulates itself based on its requirements and its desires. And I think, talking about plants from a requirement standpoint really eliminates a lot of the value added things that plants can do. So, I like to talk about trace element fertilization a lot. That these elements are not anywhere close to the radar of fertility requirements from a general agricultural posture. But there is no doubt that, what we provide to plants can either expand their ability to make what they're capable of or limit it. And, the minute we decide we have that figured out is immediately the point at which we limit the potential of the system. Plants make their own antifreezes, their own antibiotics. The flavors, the taste of crops can be affected by trace elements that are available or not. So, broadening the scope of what we think of as fertilizer is part of what we'll cover in the coming weeks, in terms of the specificity of it. But from this perspective, you can see very clearly that plants have a definite intention. Best we can do is try to get ourselves out of the way and nurture that system from the potential that it is. So there are ways in which you can affect plant availability physically. Some of these techniques are listed here. Micronization. We make a product called earth syrup that, rather than rely on the biological decomposition of organic matter, you can imagine the leaves in a forest turning into plant food. That doesn't just happen. Organic matter doesn't just melt, right? It's digested biologically and intentionally by microorganisms in the soil that take it down into an ionic form that then the plant eats. So you can bypass that on some level from a physical standpoint. Micronization is literally just the grinding and pulverization of a material. Earth syrup's like 11 different ingredients. If you open a bag, it's poof, it's almost aromatic. It's like a talcum powder consistency. So it makes it flowable and soluble on a physical standpoint. Nanotech is something that is also done in that way. There's some new products coming on the market, a nano calcium product that I'm aware of, and a nano silica product that I'm aware of. Silica is a good one to talk about in trace element fertilization. It's not considered an essential element. It's woefully deficient in soils, primarily because of the chemical stance, the bioavailability of the source of silica. Silica is abundant. I think it's the second most abundant element in Earth, other than aluminum, I believe, if I'm not wrong about that. And it's very high in clay. It's what makes up sand on a beach, and in soil for that matter. So it's everywhere, but plants can't eat the sand, right? So it's the form that the element's in that determines its availability. But using silica on a plant absolutely creates growth benefits. It allows it creates a better armor on the plant. It builds up the cell wall. The plant's stronger. It's more turgid. So just one small example of how things can be, not talked about collectively in terms of agriculture, but absolutely a benefit. I actually sell a CBD oil that is a nanotech, and the difference in it is, what you can get on the market is 10 to 20% available. What you can get out of this product is 97% bioavailable. So, from a human context, it's sold as a food. You can't make claims. I could sit here for an hour and talk about the legality of all of that, but it can be sold as a food. Cannabis can be sold as hemp, less than 0.3 THC, as long as it's imported as a food substance. But this company has actually postured it to make it available as a food, and it's creating unbelievable results for people. And primarily the benefit of it is due to the nanotech that they've applied in the chemistry of the formulation. So the same thing that can be done for something like a CBD hemp oil for human health can be done for plant health. If we think about the availability of what we're using, not only does that make it more available to the plant, but it cuts the cost and the amount that needs to be delivered, which is obviously a boon to the bottom line. My cells is a new one for me, but it's something that's worth looking into. There was a pretty good explanation at that web link down there that I'll put in the show notes. But essentially, it just takes it down to an even smaller size, and it's basically adsorbed it inside of a delivery mechanism chemically, and it protects it until the plant can grab it. So a lot of really cool science going on how to make things available. In some respects, this is a really conventional approach to agriculture without awareness. In other words, if you're growing with these materials from a chemical standpoint or a mineral standpoint, let's say, keep the vernacular right, and you're not considering the job that microbes have in soil to do this for us, we're taxing ourselves. In my experience, a foliar spray, which is the term delivered through intentional fertilization through leaves of a plant, is most conducive to targeted trace element approaches. This is back to the previous slide. delivering soluble or ionic materials to the leaf surface, you can imagine you need a lot less of the material. Now, you're not going to get as great of an uptake as you would through the root. In other words, you can't support plant growth by spraying its leaves in any experiment that I've ever seen. But it is absolutely a very good way of delivering deficient elements in a cost-effective way. Say you got an orchard and it's 1,000 acres. You got something like that, and you got to deliver a zinc application because the soil is completely deficient. Well, you can look at the cost benefit and establish that spraying this zinc supplement through the plant through its leaves would be more cost effective than amending the entire soil area with zinc. So it's a little dialogue on that. Foliar sprays were first considered and researched back at Michigan State Land Grant University back in the 50s, and the concept of a wetting agent, just wanted to bring that up. If you've heard of it and didn't know what it is, it basically emulsifies the spray. So you can imagine the water that beads up like on your car after it gets washed or waxed. The surface tension of water is causing it to hug itself, and it's only covering half the leaf. So all the wetting agent does is break down the surface tension, lay it down on the leaf, maximize the connection of the solution you've sprayed to the leaf, and increase the availability of that for the plant. So it's an electron microscope image of a stomata or stoma, opened and closed. It's kind of a cool image to think about. The plant's literally eating the air when it's regulating itself in this way. So we talked about trace elements, and this is a pretty good simple graphic. My mantra: if it's not in the soil, it's not in the plant. It's not in the plant. It's not in the people. So what I like to think about in regards to our consulting is, really a human nutrition agricultural endeavor. If we're growing plants just to grow them, we're significantly hindering what the human or the animal has access to in regards to the nutrient density that it expects, frankly. So you can see, you got macronutrients, you got, other essential plant elements, and I've added a couple that really aren't looked for in general soil testing, like silica and molybdenum. You can get those elements tested for, but typically, and nickel sometimes too, chlorine as well. The sulfur, sodium, boron, iron, manganese, zinc, and copper are pretty standard for soil testing if you've got a good lab. But to give you an idea, in North Carolina, they only test for 7 elements, I think. They're missing 3 or 4 of the elements that really need to be evaluated for just bare minimum plant fertility. And so we're experimenting on ways of creating frameworks to understand how much of these trace elements are needed so that we can begin to have a conversation on deficiency. Unfortunately, the last 100 years of agronomy not focusing on it doesn't give us a lot to work with. But that doesn't mean you can't influence this through sea energy agriculture and rock dusts. A lot of these products that people use for trace elements, all that's being done is passively. Let's ensure that it's there, that it hasn't eroded, and that we're not adding it back. So foliar sprays through the leaves are an effective way to feed plants, better targeted than general feeding approaches. So talking about the roots, this is something that most of us are already familiar with. Plants eat through their roots. If you've ever grown a plant hydroponically, it's really cool to see the root system itself. It's something that we may take for granted. Understanding the scope of a root system, quite complex in terms of what's actually happening, which is not surprising. I mean, if we just think about just simply the act of breathing as a human, it's unconscious. There's so many things biochemically that we take for granted that are just fascinating to consider. Mineral absorption through the root is just, you could spend a week in plant bio talking about one of these processes. But for example, there's things, proton pumps that are very selective towards specific elements and that regulate the balance that is needed within and outside the cell. And if you can think about each individual cell and the trillions that are in a human body, for example, or even in some plants, the scale of what's happening there is in the coordination that it takes to make it all happen, or to allow it all to happen, I should say, is tremendous. So these there's different mechanisms. They can trade off. Where they're going to bring in a nitrate along with a hydrogen. It can be, typically what's called active transport is conducted against an energetic gradient. It's a bit like what happens in photosynthesis, where we're building up the ATP in order to use it for energy somewhere else. It's harnessing that from the sun's rays and the energy that's absorbed in through the chlorophyll in that process. That energy is then leveraged to do all sorts of different things. And these are just some quick visuals of these processes. This is not a passive process. It's a very active and deliberate process from a cellular standpoint. And this is another image. This one is the sodium potassium pump. So you can see, outside the cell, the plant needs to intake potassium, and they do it by kind of a bait and switch. You see the ATP coming through here. You see the ATP, the energy being used to swap those elements. And this really gets into the balance of our diet, and a lot of that is unconscious. We kind of eat from a caloric standpoint, but the idea is that our diet supports the balance of the elements that our cells need to coordinate themselves into carrying out living systems. Thankfully so. But it's really kind of fascinating to think about the specific activities. I'm not going to go into the specifics of the pumps and things like that. I don't know that that's entirely relevant, but it's good to be aware that plants are working in ways that are very easy to take for granted. So what is plant food? Plants do make their own food. They make their own carbohydrates, right? They make glucose, and then the respiration cycle breaks that glucose down. That's the result of photosynthesis into all of the metabolites that plants need. But there are requirements from outside the plant in order for that glucose photosynthetic process to have the materials to then break down all of and manufacture all of the metabolites through the citric acid cycle and the Krebs cycle and all these different cycles to make plants. So, a little bit rudimentary, but we're going to go through each one in a little bit more complexity. As general as you can make it, plant food is air, light, water, and ions. So just looking at air first, air is maybe more complex than we realize as well. It's always interesting to me, like in hydroponics or brewing, when people are talking about dissolved oxygen. Obviously, you could make an argument oxygen is the most important element. Of course, based on the law of the minimum, you could say they're all equally as important within their relevance. But air, I'm not sure people realize that. What's krypton? Is that Superman? It's like xenon and neon. I mean, trace elements, but air is not air unless it's what it is. You can't manufacture air. It'd be kind of like trying to turn a pond into the ocean. Like, where do you start, and how do you manufacture the balance and the momentum that system has? It's really difficult to engineer, and then on some levels, that's kind of what we're talking about in bioenergetic agriculture. We're talking about regenerative agriculture. How do we kickstart the system to work for us at its utmost capacity? And ironically, a lot of agriculture works against these balances and processes. So it's pretty interesting to see that the majority of air is nitrogen. Nitrogen is a very influential element. In the energetic conversation that we'll have in the future, we'll talk a little bit about, its influence. And we tend to think of it as just a fertilizer. But the reason for that is that we disrupted the system so that it can't really access it on its own. There's nitrogen fixing bacteria that can measurably increase the nitrogen capacity of a system and mitigate the need to fertilize. 4 fertilizations of nitrogen a year are taken away from the lawn if you bag your lawn clippings and put them on the curb. So, it's not surprising that we need to come back and replace that and supplement it with a fertilizer. I'm not judging fertilizer. I mean, it's absolutely vital, especially in sandy soil conditions where the exchange capacity is not large enough to support the plant growth. But generating some benefit out of the soil's ability to sequester this is part of the conversation here. If you're aware of that, it's probably from the context of legumes, and the rhizobacteria that can coordinate with plants and fix nitrogen with peas, and clover does that really well. So that can also be, when you start to see clover in a field, an indication that the soil lacks biological activity conducive to fixing the amount of nitrogen that plants need to grow. So interesting to look at the breakdown of air. It's not just about oxygen; it's about the balance of those elements in total. So looking at the gas exchange, this is a kind of a simple image, but carbon dioxide goes in, the water and oxygen come out. Thankfully, so. We just got done talking about another level of complexity here and relevance is the ability to eat through the tissue. But in this context, we're talking about air. You can see a little bit more detail in this, just from an image standpoint. But essentially, those stoma are open during the day when the plant's photosynthesizing. They close typically at night when they're looking to retain the balance that they have to generate through the day period while they're photosynthesizing. And again, there's an innate breathing going on there, but there's absolutely action towards what plants require and desire to grow. Gas exchange can also occur through the stems of plants. There's a term called a lenticel, and you can see the image there on the left. It's just basically a broken portion of the tissue. It just aids in the breathability of the plant. The extreme to that is certain, like mangroves, certain trees in very wet areas that have adapted to be able to have kind of vesicular structures that come up out of the soil in order to access air directly. This is kind of a small context in that regard, but plants can breathe, if need be, through their tissues as well. It's not, if a plant's not adapted to that kind of environment, and you get wet feet. I experienced that on the farm that we ran locally here for 3 seasons, and the soil wasn't draining properly, and the first crop that we planted, we lost a whole crop of garlic. And it was a stinger. It was like $3,500 in garlic that was just planted in the wrong portion of the field. And in a lot of ways, we were just getting our feet wet, no pun intended, and learning as we go. But those are costly mistakes, and certain plants just can't tolerate wet feet, and it stimulates a lack of respiration, a lack of the ability of the plant to breathe, and that's when disease attacks. So that idea of creating the porosity in the soil can also be looked at from a mineral context. A high magnesium content in the soil, because magnesium is smaller in terms of its ionic radius than calcium, which is a bigger molecule with double positive charge. Think about the calcium like a beach ball and the magnesium like a bowling ball. So what happens is the soil with high magnesium doesn't have a lot of porosity, and you get a really hard pan scenario. You see that a lot in clay soils that are low in calcium, and you just can't get water through it. And you can change that simply by soil testing and amending with the proper calcium to magnesium ratio. So there's a lot of different ways into that idea, but plants want to breathe. This is how they do it. Our goal is to try to set the situation up so that they can be most successful. And then the extreme of this is epiphytes. Many of the orchid species that you're used to seeing with roots growing in the air are, this one here on the left is simply a replication of what it would experience in nature, like on the bark of a tree. But they're fixing everything that they need from the air, which is pretty fascinating. It kind of, creates a bit of a disconnect in regards to how we consider plants eating to begin with. I got done saying a minute ago that plants can't survive through foliar sprays and through eating through their leaves, but again, here's that outlier. I guess I'm too busy trying to compartmentalize nature, but epiphytes can survive out of the air, and Spanish moss is another example. We have a lot of that around here. Again, I guess there's kind of a strange scenario around us, and I've always been fascinated by Spanish moss, and it actually ends up fixing more phosphorus than is available. for it to fix. It really is alchemy. If you look at the breakdown of air, and I was just making sure I wasn't in the wrong spot there. There's no phosphorus measured in the air. So how does the Spanish moss end up with measurable phosphorus? It's an interesting question. I don't have an answer. It's a bit like in a hydroponic posture where you have 17 elements in water, 17 elements in the fertilizer and clean water, and it doesn't take much to imagine the plant ends up with more than 17 elements in it. How does that happen? It's a really, really good question. If I had an R&D budget that was really significant, I'd get to work trying to figure that out. But regardless, considering how plants have access to air depending on how they grow is something that can absolutely enhance your crop production, your plant growth. So just to talk about light a little bit, I've got a good level of expertise in lighting from my garden center days. We consulted with a lot of hydroponic growers. I was actually in downtown Wilmington just today talking to an outfit that wanted to put an urban farm in a basement of a new building they were building. And they had a bunch of restaurants they were developing around it. And they liked the idea of feeding the restaurants and creating some buzz and urban farm juju for them in the local community. And you get into talking about, well, how do you get the plants to grow? And they were hip to LEDs from an efficiency standpoint, but hadn't considered the full plethora and spectrum of what plants need to grow. It's LEDs are really relevant. Of course they're efficient, but they're efficient because singular wavelengths are chosen. Whereas if you work with what's called an HID, like a metal highlighter of high pressure sodium, think like street light, ball field kind of thing, or a fluorescent. Both of those fluorescent and HIDs contain the entire spectrum. And the technology is really in how to manipulate the gas in the arc tubes to emit the spectrums that we want versus the ones that we don't. And we know a lot, but just like every other endeavor, into a living system, the further we look, the more we got to figure out. So, that's the case. There's a lot of progress being made, but you can see on this chart, this is, current knowledge around the activity of chlorophyll at different wavelengths. So what you'd see in grow lights is peaks where you got the peaks in the photosynthetic requirement. There's a term called PAR watts, photosynthetically active radiation. And it's a conceptual metric of measuring how much light out of a source is plant usable. It gets a little squirrely because it's conceptual at this point, again, because we haven't defined it. But there's things like foot candles or lumens, which are standard calibrations, but they're to a human eye, not to a plant chlorophyll. So you could have a light source that has a tremendous output, lumen output, but if it's not in the right wavelengths, you're missing your mark. And that's really why you buy a grow light versus just a light from Lowe's or a big box store or something like that. Nevertheless, this Kelvin rating down here is, the higher the Kelvin rating, the more blue. So you're typically looking for, these peaks in photosynthesis. And if you buy a good grow light, they've really done the hard part for you. It's worth considering that this visible spectrum we're talking about is a very small portion of the electromagnetic spectrum. And there's a lot that's not known about how these outlying wavelengths, either larger or smaller, influence plant growth positively or negatively. The goal is always to try to replicate the sun. There's an index called the CRI, Color Rendering Index. It's somewhat conceptual, but 100 being the sun, 0 being nothing. And the highest that I've seen on a artificial lamp for plant growth is about an 88. So that's pretty high, but it's safe to say that you could never replace the sun, even, especially in spirit, but, any kind of physical wavelength. We can make it better, but it's, the sun's always going to be best. So I mentioned this earlier, but it's worth mentioning kind of as an outlier, plants moving. You can really see this on your crops. If you have your pepper plants like this in the morning, when you come home and in the afternoon, they're going to be like that, right? They're almost like the solar panel idea. And it's really interesting to see how that works from a hormonal perspective. These little dots are hormones, and they can stimulate the length of the cell based on where the sun's hitting and not. So that IAA hormone either concentrates on the side that it concentrates on the side that you want to along, so that the plant moves towards where the sun is. I mean, if that's not intelligence, I don't know what is. That's pretty fascinating. So, we talked about air, we talked about light, talk a little bit about water. I won't spend a whole lot of time on this. I could. This is a great fascination of mine. Spent many years researching and reading and investigating and pondering water as a substance. It's so much more than the name that we've given it. There's one word for it, but water's never the same. And it's not only from what it holds, it's the universal solvent, right? It made the Grand Canyon. So it's looking to pick up things and carry them around. That's a lot of what water does, physically and also vibrationally. And so the molecular structure of the water actually influences its ability to operate in this capacity. We tend to think about water very simply in terms of hydration. The majority of people, regardless of whether you drink enough water on a daily basis, are dehydrated. And it's implicated in many degenerative diseases that, it's tough to connect the dot completely from a therapeutic standpoint. But anecdotally, I've seen water change people's lives when they change the access that they have. I drink out of this thing called a flaska. It's a glass bottle, and it's from Slovenia, and they're amazing drinking water experiences. But they actually impregnate a frequency into the water that is projected into the water you put into the vessel, and changes the molecular structure to the extent that it can increase the cellular hydration. So, I've included some images of how water moves here. You can influence water on a molecular level through form, such as allowing it to implode on itself, which is why a river meanders. Or you can also do it through frequency, through affecting the vibrations of if you've ever heard of a gem elixir or a flower essence. That's what they're leveraging there. They're taking very high resonant materials and placing them in water so that the water can orient itself to those vibrations, kind of opens the water up, if you will. So, the reason, and, one way of looking into this is that cells drink water through what's called aquaporins. And the Nobel Prize in Chemistry was, I think it was 2001, maybe 2003. Dr. Peter Agree. He discovered the aquaporin channel in cells. And it turns out, upon further research, that basically every living cell has aquaporin channels. And the gist of it is that they drink water one molecule at a time. So, it's always on some level going to be an oversimplification. But if the hydrogen bonding of the water is too strong, then the clustering of the water bypasses the cell. So what that would mean is we're told to drink half our weight in ounces of water a day to not be dehydrated. It's kind of a significant amount of water if you do the math for your weight. But even if you do that, if the structure of the water is not conducive to cellular hydration, the water just irrigates your kidneys, right? It doesn't hydrate your cells. So project that onto plant growth. If the structure of water is not right, the amount of fertilizer that we need to use to deliver it to the sweet spot inside the cell is significantly more than if the water could flow in naturally. So that idea is oversimplified, but the structure of water can just so we understand the chemistry behind water. You've got hydrogen bonding, you've got a polar molecule. The hydrogen is positively charged, the oxygen is negative. Most everybody is familiar with the polarity of water. It's called a dipole moment. And that positive and negative orientation allows it to combine with just about everything, if not everything, as long as it's soluble on that level. It also creates a phenomenon of attraction to itself, which is called hydrogen bonding. That's why you can get, water striders on a lake or a, meniscus in a glass. Water has an ability to hug itself. So when we use the wetting agent from earlier, what we're doing is just breaking down the tightness of that bond. We're making water wetter, if you will. And you can do that through a wetting agent. You can also do it at the same time, running it through a microbe maker system, for example, and imploding the water, or just stirring it back and forth in a bucket. You can bypass the need for a wetting agent doing that kind of thing. So, water is, we'll spend a whole session, maybe a couple, on water in the future. But water is a primary nutrient, I like to call it. It's not just a delivery mechanism. It's actually required by plants to bring nutrition and oxygen into cells and then carry away the toxins. And if it can't get in the cell, it cannot do that work. So considering your water is something that can really step your game up in a big way. So we'll talk about the elements or the ions. This is the realm of what people are talking about when they say fertilization. There is and I think not next week, but the week after, we'll talk about soil testing, and we'll look at the work of Dr. William Albrecht and the mineral balance that he came to in his research back in the 40s and 50s at University of Missouri. And he basically did crop trials and soil testing and manipulated the ability of the soil to hold nutrition. It's called the cation exchange capacity. There's also an ability, what we'll call the anion exchange capacity in soil, and it can get quite complicated, so I won't go into that today. But nevertheless, the soil has an ability to hold nutrition. Think about hydroponics as an instant exchange capacity. You're bringing everything in a soluble form, which is, in a real sense, what most people do in their gardens, right? They're not really paying attention to the balance in the soil. They're just bringing the food the plant needs to grow. They're treating the soil like a hydroponic system, in a direct way of saying it. And you can get results doing that. On a business commercial scale, you're going to pay an arm and a leg to do it. So, it pays itself over and over to look into your soil and generate the balance that the soil needs and open up its ability to be soil. But looking at it from an elemental standpoint, so we'll get into the organic versus artificial in some depth next week. But you can see here you have an atom when it loses electrons in its ionic form can be a cation, a positive element, or an anion, a negative element. Depending on what element you're working with determines its chemistry. The combination of those, like sodium chloride, is what we'll call a molecule, right? A compound in that sense. So there's we've talked about the law of the minimum, but just to refresh, chain is only as strong as its weakest link. Everything being adequate in the base saturation and the ability of the soil to hold its balance, or frankly, in a hydroponic nutrient that's intended to be used in pure water, it's bringing that balance. If everything is perfect except for one element that's required, the whole system is limited. So it's really important to have an understanding around specific elements and how they work. And generally speaking, unless you're amending from a soil test perspective or you're kind of a progressive hydroponic grower, you're typically not dealing with singular element fertilizers. I always advise against people, there's a lot of people out there that use Epsom salts for fertilizing their tomatoes every year. And, while the intention is good, Epsom salts is magnesium sulfate. It's two elements. You can create just as much imbalance using that as you can helping. It really is not advisable to use singular element products like superphosphates and even lawn nitrogen applications, things like that, unless you've done some soil testing and you understand that you need to account for the deficiency. The nitrogen makes some sense because we actually don't even test for nitrogen on our basic soil testing because we can get all of that from the environment and the air setting the situation up correctly. But I wanted to walk through just kind of an articulation of how to think about these elements in terms of the ionic discussion that we're having around what plants eat. It's one thing to talk about the diversity of elements, which we've been doing. You got the macronutrients, the micronutrients, and the trace elements. Required in smaller amounts, and then beneficial but not required. It's also important to talk about the form the element is in. Silica being a perfect example. You can have all the silica in the world in your soil as sand, but the plants aren't able to access it nutritionally. So there's that not only comes from the molecule or the compound status of that element, but it can also be accomplished through what's called isotopes. You might remember that from chemistry class. An isotope is just simply a different form of the same element. And it may be due to an extra proton or, something that has changed the makeup in chemistry of the ion, yet it's still identified based on the laws of chemistry that we've established. So, without getting into science class, essentially the same element can be represented in different ways within natural systems. Magnesium has 3 different forms it takes. Nickel has 5. I think carbon has 6. So this isotope thing, the complexity of what you get from an organic form of nutrition is a lot higher than what you'll find from a conventional source, which is typically, if it's pure, a pharmaceutical grade form of that ion. And a good way of looking at that is urea, nitrogen, not very bioavailable. It's what accounts for the majority of what you see in budget products like Miracle-Gros and things like that. They have a really high nitrogen number, but it's not in the form of ammoniacal nitrogen or nitrate nitrogen, and a lot of it is in the urea form. So it's just not available to the plant. It's also, in the epiphyte conversation, it's always advised to use a nitrate form of nitrogen as opposed to the ammoniacal. So, you can get into parsing this in different ways. And then there's also the discussion of the balance and the ratio of the elements to each other, and we're talking loosely about that in terms of the diversity. But there's antagonistic ions and synergistic ions. So you can see, this is called Mulder's chart, and it doesn't really give you a whole lot of detail. It's more of just an influential schematic where you can see certain elements play off of each other. Boron needs to be 1/1000th of calcium to be available, for calcium to be available. So you can see, the association there is if boron is deficient, calcium is deficient. They can work against each other, even though they can be postured to work with each other. So if this is kind of an anecdotal, people building on the backs of others over the years sort of thing. But it's worth considering the way in which certain elements influence others. In our soil testing talk, I'll show you some of the detail that we get into when we're analyzing these ratios from our fertility management service perspective, and it's pretty interesting. So just wanted to show you a couple of leaf images from deficient elements. 99% of the time, if people see yellowing leaves, they say it's a nitrogen deficiency, and a lot of the times it can be. But nitrogen, the weight put on nitrogen, on one hand, is understandable because we're really working against this system to be able to generate it. But it's also a oversimplification of plants, and I'm not going to go through every element here. I think we're kind of getting short on time, and I wanted to reference outside the plant to set up next week a little bit before we finish here. But so this is a tomato plant with a nitrogen deficiency. You can see some of the relevance of nitrogen. Every element's going to have critical, if it's essential, it's going to have a critical relevance in the plant. Trace elements tend to work by making other elements work better and increasing the value of that nutrient density and medicinal value of the crop that you're growing. So you can spray nitrogen on a deficient plant and it will recover. It shows in the old growth first because plants can translocate the nitrogen within the plant and they tend to prioritize. So if you've got a really aggressively grown tomato plant, you might find that the old growth that's not in the sun anymore is being sacrificed, and you can lop it off, in my opinion, just so it doesn't stress you out looking at it. And that happens a lot when you're growing the plant aggressively. It doesn't necessarily mean the plant is struggling, even though you'd like to see uniform growth. But it's important to note that nitrogen can be moved. Same with phosphorus. You can see this in old growth first. Notice that it's not yellowing, it's curling. So, you can get into the relevance of phosphorus. Again, every element is going to have that direct relevance if it's a essential element. But a lot of times you don't articulate phosphorus. It's just a smaller plant, right? It's the plant's growing, but it's dwarf. There's no other explanation for it. A lot of times that's a phosphorus deficiency. Potassium, you tend to see scorched leaves. You have the yellowing is called chlorosis, and the dying of the tissue is called necrosis. So different from phosphorus and nitrogen, you can't really recover from a potassium deficiency. That necrotic tissue there is sacrificed. It's never going to reconstitute. So the NPK obviously are the macronutrients. You need them in most abundance, and you're going to see their deficiencies most obviously when they're deficient. Calcium's the same way. You can kind of bad image, but you can kind of tell it's somewhat similar to the potassium. So without soil testing or tissue analysis, it's really kind of just kind of a game to try to figure out what your deficiency is. you can also you can flip that around and try a calcium supplement. Most every fertilizer line in the hydroponic world has a calcium supplement because it's quite variable in regards to its requirements. Some plants, even of the strain, same type of plant, different strains, some strains, might demand it, some want it, and others don't. And it's the same plant, right? But calcium, another one you can make the argument is the most important. It's, metabolically what's happening with blossom end rot with tomatoes. It is a calcium deficiency at the end of the fruit. It's not always a calcium deficiency in the soil. Could be the boron that I mentioned earlier. So it's never, there's never a straight line here. But again, you can, all of these elements are mobile within the plant. Calcium tends to be very low. And I wanted to highlight iron because this one's a bit of an outlier. All of the other ones can translocate these elements within the plant. Iron is not that way. Once it's fixed in the plant, it doesn't go anywhere. It's non-mobile. So it's actually fairly easy to determine an iron deficiency because you see it in the new growth as opposed to the old growth. The plant can't prioritize. So that being said, it's interesting to look through these kinds of things. But what you can really get down to in terms of looking at a plant and knowing what's wrong with it, it's a bit like looking at your soil and trying to figure out its deficiencies, right? You can kind of guess and you can experiment. The only really the way to know is to do some tissue analysis or some soil testing. So just wanted to kind of, we're talking about how plants eat, and they access the air, the light, the water, the ions, but they're not alone. And it's moving out into the soil is kind of the next phase of conversation that we'll have. And it's important to understand that the plants, it's not a passive being. It's actually creating relationships in the soil. We'll call the soil area the rhizosphere. That term was coined by Lawrence Hiltner in 1904. It's, for lack of a better description, the interface of the soil and the root, where you see, microbe symbiosis. Microbes are attracted by exudates. More than half the energy that plants generate through photosynthesis is pushed out of the roots to attract microbes that help them eat, protect them from disease, do all sorts of valuable things that we spend a lot of time working against. But a good way of kind of illustrating this is show you a couple of images. You can see the endorhizosphere is actually part of the plant tissue. You have the rhizoplane, which is the interface itself, and then the ectorhizosphere. That collectively is called the rhizosphere. So these root hairs move out into the soil. They push these sugar meals out into the soil, and you can see, here you've got an endomycorrhizae that has actually pierced the tissue of the plant. The plant feeds this organism, and in return, through the sugars, and then in return, the organism acts as an extension of the root. Frankly, without the plant having to expend the energy to grow it. It's free roots, right? So Mycorrhizae fungi are very well known agriculturally. It's a drop in the bucket of the food web. They just happen to be a very selective and identifiable strain of fungi. And they can't replicate in a compost tea. You can't grow them without the plant root present. But you can actually roll your seed in it or stamp your clone roots in it, and it'll travel with the root. So you have endomycorrhizae, that's kind of a root extension, and then you have ectomycorrhizae that don't really contribute towards the growth of the plant, but are more charged with protecting the plant from disease. And in a good mycorrhizal product, you'll get both of those, and they tend to include every strain that is known and available, so that the one that's selected towards the crop that you're growing will predominate, and the ones that aren't needed will die away. So here's some images of mycorrhizal fungi at the root. It's kind of a cool image there on the left, and on the right, you can kind of get a mental image that, say 30 to 50% of that root surface there is actually fungal hyphae that has penetrated the plant root and is increasing the surface area of the plant's ability to access nutrition, and therefore it can concentrate on growing up instead of down. And I mean, plants have to grow roots, but they don't really want to, right? They want to produce seed and reproduce. So as much, I like to think about the bottlenecks of ice ages. You've got this tremendous stress towards, terrestrial growth, and the climate's changing, and any plant that can figure out how to generate teammates from its environment wins the day, and they come out the other side. So what you have is basically 99.9% of plant species take advantage of mycorrhizal fungi. They don't have to have them there to grow, but they want them. And you can kind of see, some of that influence. I've done turf experiments myself, just get a container with mycorrhizae and one without, same soil, same everything else, and watch what happens to your plant. It looks a little bit like the bottom right image there. So, really quite impressive. So, we'll end with, just want to show you this quick video, just because it's, nothing too profound, but it is in just kind of a visual of plants in motion. And what you'll notice, as the plants, it's always, time lapse is amazing. Did you see the flashes of fungi happening down there? There's a rhythm to the plant growth and the fungi, and they're working together, and they get this synergy. And you can actually, on the biological conversation, part of this conversation, we'll talk a little bit about research that has been conducted over 10, 15, 20-year period that shows the development of an ecosystem biologically. And it's a bit like putting a bunch of strangers in, a new community. It takes time for them to figure out their strengths and their weaknesses and their associations and build their community, So, I love this video because you can just, bam, fly. I mean, what's happening there? Who knows? But the intelligence of the system is integrating itself, and the plant and the microbes are becoming very good friends, and they're figuring out how to leverage each other to accomplish what they want to do in their life. It's kind of fun to create a human context around these things. I think that it actually helps us understand it a little bit better. So not every day you get to see roots growing like that. It's kind of cool. So let's see. So, to kind of in closing, it's really important to take an ecosystem mindset and approach, no matter how far you drill down on the specificity of what we're talking about. You can see today, plants innately have in them the ability to operate as a plant. You on one hand could say it's our responsibility to bring that to a plant if you're in a hydroponic application, and flip to that, you could say it's our responsibility to try to get ourselves out of the way as well as we can in a more organic situation. So, next week we'll really kind of create an expose around that and start to talk about, forms of fertility. What's the difference between organic and hydroponic in terms of the ion that comes from hydroponic versus the ion generated from a microbe. And then we'll move more into some hydroponic methods so that you can kind of conceptualize, whether that's something you may want to try, or, and why to do what sort of method based on your situation. I mentioned the soil testing. We'll talk about some trace element, fertilization, sea energy agriculture. And then, once we've kind of exhausted the conversation around the mineral component of bioenergetics, we'll move more into the biological, and we'll keep moving forward. So that wraps up today. If there's any questions, I'm happy to take them.